Let's move on to item J, report acceptance, review of Cathodic Protection System at Valdez Marine Terminal, and that's with Austin Love and Keith Boswell. The floor is yours, Austin.
All right, thank you, Robert. Everybody hear me?
Gotcha.
All right. So if the information that we're going to be talking about today is in section 4-2 or page 96 of your board meeting packet. So if you wanted to flip there while we're going through this. My name is Austin Love. I'm a project manager for the council based in Valdez, and I've been working with Keith Boswell, who's on the line from National Pipeline Services on this project. Keith is our subject matter expert in the area of cathodic protection. And at the end of, Keith's going to be giving a presentation about the work that he's done for us, looking at CP systems at the terminal. And at the end of Keith's presentation, we're asking that the board accept Keith's report in National Pipeline Services report, to accept the report as meeting the terms of the contract, but also, and I think equally important or more important, to share that information with Alyeska, state and federal regulators, with asking them to consider the recommendations that Keith is going to be going over, and hopefully taking appropriate action on the recommendations by Keith. And with that, I'll let Keith take the helm.
Thank you, Austin, and thank you to the committee for allowing me to take this time. Let me try to share my screen here. Can everyone see this presentation?
Looks good, Keith.
All right, well, just as Austin had said, my presentation here is going to be focused on the cathodic protection of the crude piping system at the Valdez Marine Terminal. Just a little background. I mean, this project really started in 2019. It commenced with a site visit by myself in late September 2019, and in which I got an opportunity to meet with the Alyeska corrosion and cathodic protection personnel, and get their inquiry, ask some questions about their cathodic protection systems, and get a firsthand visual and knowledge of their systems that they're operating there at VMT. And then the next process was to try to get some additional data, some historical data that they've collected throughout the time. And with COVID and a few other factors that kind of crept up, those data requests kept getting pushed out, and it was really early 2021 that we really got enough substantial data to make an assessment on the cathodic protection system here at VMT. So with that, I mean, my general agenda for today is going to be a basic introduction of what cathodic protection is, basically a quick cathodic protection 101 course and crash course for everyone to just kind of get a quick background of what it is and how it applies, and hopefully enough knowledge to comprehend what my presentation entails today. I will review what those cathodic protection systems at VMT for the crude piping systems consists of, how those systems are monitored, and then my general assessment and opinions on the overall cathodic protection at VMT. So looking at cathodic protection basics, this first slide is a basic corrosion cell that parlays into cathodic protection. So when we look at a corrosion cell, when we have two dissimilar metals, and in this case, we're showing steel and copper, inherently one of those metals is more active than the other metal. And when they are connected through some kind of metallic path and some kind of electrolytes, then we have the components for a corrosion cell to occur. And what happens is that material that's more active than the other metal becomes the anode, in which that anode then essentially gives up its electrons and essentially corrodes, and in essence then protects our cathode or that other metal that's more noble or less active. Chemically, what happens, I mean, we can get real technical, but we basically change the voltage potential or voltage level of what those anodes and cathodes are. And at the surface of this cathode, we build up a level of hydrogen polarization that occurs visually. I mean, you can almost, I always kind of represent it as a little tiny bubbles that builds a film on that cathode. And that effectively helps change that voltage potential, makes it cathodic, and offers that level of protection to structure to that cathode. So an impressed current or a cathodic protection system kind of utilizes that basic corrosion cell in which we introduce some kind of sacrificial metal or an alternate metal into the soil or into a water, which we want to corrode. So we want to force that metal to become the anode, so that the structure we're trying to protect, in this case our crude piping system, in turn becomes our cathode. And we energize those in an impressed current system. We energize it with this rectifier, which just basically takes your AC voltage, converts it to a DC voltage, and that DC voltage is what energizes our anodes in this system. And then in turn produces conventional current flow from the anode to our cathode, to our piping, which in turn protects that piping from corrosion. At VMT, in 2018, Alieska introduced a linear continuous anode system to help protect the crude piping within VMT. This system was installed to help supplement the existing cathodic protection systems that they had at the facility. Those systems being more remote type cathodic protection systems. And through their testing and analysis, they determined that they just weren't getting enough cathodic protection out of those systems. So they added in this linear protection to kind of give it a more discrete protection specifically to that crude piping, and a more direct source and look of cathodic protection that goes directly to that. So same concept. It's just a linear anode that's comprised of actually a polymer type anode, but it's powered by a rectifier, same kind of system, and it offers that cathodic protection. This here is a general overview of the VMT terminal. We have our docking berths here, 1, 3. We have our tank farm, our east tank farm, our west tank farm, and the crude piping system really begins here at the east metering facility, traverses across the terminal to the west metering facility. That crude piping, there's an A and B header system. So there's 2 pipelines. They're 8-inch in diameter, and the effective essential length of this piping system then is 3,500 feet. Monitoring of the cathodic protection is kind of twofold. The first set of monitoring is to monitor those rectifiers, that being the power sources to the cathodic protection systems. And those are monitored 6 times a year, not to exceed 2.5 months. So the premise and thought there is to make sure there's power to those rectifiers. If there's no power, then we don't have any cathodic protection on those crude pipings. So they're monitored on a regular basis to make sure they're operational and that they're within their set guidance of limits of what they want those systems to operate at. At VMT, LESCA actually utilizes a remote monitoring system that continuously monitors these rectifiers. And they have limits set, so upper and lower limits. So if they don't have power to that rectifier, that remote monitor recognizes that, sends an alarm to the corrosion personnel there at LESCA. And so they're made aware of it, and they can do some investigation as to why there's no power. Likewise, if it falls out of tolerance of their lower alarm limits, or maybe exceed their upper, it gives them another alarm in which they can go further and investigate. So it's a nice, great tool to have for monitoring purposes, and it's very, very effective. The other aspect for monitoring is to obtain a voltage potential of that crude piping to determine how effective the cathodic protection system is actually working. So this voltage potential basically gives us a guideline of whether it's meeting a set criteria that identifies what the adequacy of cathodic protection is. So these are performed annually by LESCA, and the test points are just random locations along the crude piping system. It's there's basically a set of wires that are connected to the pipe, brought into some above ground feature or test point in order to make a connection to the pipe and record that voltage potential. They can utilize also any valves or above ground appurtenances that, as long as they can make a metallic connection to the structure, we can get a single point reading at that location. So, here's kind of an example of not really the test station at VMT, but a typical test station. Just there's wire brought into that conduit to the post, and we can take a reading. The other type of survey that can be utilized is a close interval survey, which is a reading taken essentially every 2.5, maybe 5, or even 10 feet along the crude piping system. And that allows a continuous profile of what the actual potentials are between these individual test points that they're monitoring on an annual basis. So it gives a little bit more complete picture of what's happening in between points that they're monitoring, and tells a little bit better story of how adequately protected those piping systems are. So, and this picture here just kind of shows a person. They have a backpack with the wire reel, so they make a connection to a valve or the test point, and they string that wire along so they maintain continuous contact to the pipe. And then they have reference electrodes that are utilized to measure that voltage potential with the voltmeter, and just walk the pipe and stick the reference in the ground and then obtain that potential. Criterion that are utilized within the industry to show and prove adequacy of cathodic protection. First criterion is having a polarized potential of 0.85 volts with the cathodic protection on. However, there's some caveat to that potential, because with your cathodic protection on, you have current flowing through the soil, you have resistance of that soil, and so inherently you have some voltage error built into that on reading. So to eliminate those voltage errors, the current sources that provide cathodic protection to that structure, all those current sources are synchronously turned on and off, and on a set cycle, and maybe like a 3 second on, 1 second off type cycle, and just continuously throughout so that they can still obtain a non-potential, but then as soon as those current sources turn off, we can obtain, I'll call it an instant off, or really that's the polarized potential of that pipe. So, as I discussed earlier, that cathode builds up that polarization as a chemical process, a result of cathodic protection. That level of polarization is what really tells us how adequately protected we are. So primarily this criteria is the 0.85 polarized potential criterion. If we have areas that those polarized potentials are less than that 0.85, there's a supplemental criteria called the 100 millivolt polarization, and that effectively measures that level of polarization by allowing the cathodic protection systems to remain off for an extended period of time. And effectively what happens is that polarization that's built up on that structure starts to dissipate and depolarize to, at some point, if you leave it off long enough, it will come down to its natural or its native potential of what that steel or whatever that metal is in that environment. So we can measure that level of polarization by comparing that depolarized potential or that native potential back to what the polarized potential was that we measured. And I'll kind of get into this here in the next slide here with some examples. So this is what you typically would see during an annual type inspection, where we had have our different test points 1, 2, 3, and 4. Different varying years of readings. So in this case, 2016 to 18. Here we have our on potential. So this is with our cathodic protection on. And then we have our off, or that instant off, or the polarized potential. So this is when we interrupt those current sources, and as soon as those turn off, we record what that polarized potential is. This effective dipole potential here, this voltage, what they're using there is sometime back in some history, they recorded, they allowed their system to depolarize, maybe get down to some native state or some depolarized state, and they recorded those potentials. So they're utilizing that as their depolarized potential. And then for those areas where maybe, like in this case, if there was a potential less negative than the 0.85, they're able to compare that to this dipole potential, and this calculated shift is the difference between those two values. So 144 millivolts or 0.144 volts. So that's more than 100 millivolts. So they're effectively, showing that they are effectively cathodically protected at that point. So I have a few other cells here highlighted that's in yellow here that are pretty excessive as far as a polarized potential is. There's been studies performed within the industry, and for steel that's, it's empirically not possible to polarize steel to a potential more negative than 0.15 volts. So when we see some readings like this where they're excessively more negative than 1.15 volts, that leads us to believe that there's probably some error in that measurement that is causing that excessive potential. So there's a concern here with some of the data that's that Alyeska has been collecting, that they've got some elevated polarized potentials like this, and they kind of recognized it in notes that they've made that because of the proximity of that linear anode, that that they're probably being influenced by that linear anode even when it turns off. So they acknowledge it, but that was kind of, that's to the extent that they carried it out, at least at that time. So the concern here is, if we have an error in these set of readings here, do we carry that same kind of error in this reading over here? So there's some concern there with some of the quality of that data. The other concern that has come up with us is, the effective depol, utilizing some old historical data is really not prudent in the really true essence of what the criteria and regulations are really trying to do. Ideally, when you experience a situation where your polarized potential is less negative than your 0.85, then at that time is when you should go through and then do some additional testing and depolarize your system, turn those rectifiers and then press current systems off, and come up with a new effective depolarized potential to compare. So concern is, conditions can change. This depolarized potential could change through time. So, a more prudent effort on their part to really utilize that 100 millivolt criteria, I think is the point to be made here. This here is an example of a close funnel survey. So this kind of shows, between your test points where it's a discrete location that you're taking a reading, a close funnel survey, like I said before, gives you a profile of what those readings look like between your different test points. So this example here, this is 800 feet of profile that we're looking at. And the blue is our on potential. The green is that instant off or that polarized potential. And then this red line is that 0.85 criteria. So any areas where that off potential is less negative than 0.85 tells us that we're not meeting that 0.85 criteria and we may be unprotected at that location. So without doing further testing, where you could do a depolarized survey across there to see if you have 100 millivolts polarization, but there's, that's our threshold. That's what we're looking for. So in looking at some of the data that there was some close funnel survey done back in 2018 by Alyeska. Some of the same concerns I had regarding their annual test point survey, where they had elevated polarized potentials, was seen also in the close funnel survey data, where they had polarized potentials negative 1.5 to negative 1.8 volts, which, there definitely is some kind of error in that reading yet. And they did have a small section of polarized potentials that were below 0.85, below criteria. So, which they've since have said they have addressed, but I haven't seen the actual data to actually confirm or deny whether that's been taken care of. But my general assessment of things, this table kind of just shows here. So looking at the cathodic protection system designs that they have out there for the crude piping system, with the addition of the linear anode to help supplement their existing cathodic protection systems, is solid, very good. So I'm happy with the system designs they have so far. Their cathodic protection system, their procedures, and really their annual survey reporting their annual survey reports are very thorough, very detailed, and so the procedures are really good. I have a few minor recommendations in the reports, just for suggestion improvements or clarification on some of those procedures. The cathodic protection rectifier monitoring, because of the remote monitoring that they utilize, I mean, their monitoring of those cathodic protection systems are really excellent, actually. Their cathodic protection systems, there is really at this point is the weak point a little bit. I mean, it's marginal to that effect. There's some things they can do to further enhance and troubleshoot and try to get a better reading and eliminate some of those errors that they're encountering in their surveys. And my latest discussions with the corrosion professionals over there at Alyeska is, I mean, it sounds like they are taking some of those actions and doing some further testing and analysis of their other cycles of how long they're turning their rectifier or impressed current systems off when they do those kind of surveys. So that could help in eliminating some of those errors, but it sounds like it's a work in progress yet. But I mean, overall, I mean, I still feel like, I mean, they have a good grasp of their cathodic protection system. And I mean, I think they're doing a pretty good job continuing going forward. But and then lastly, here's, I mean, just some of my key recommendations from the reports is to do some of that alternative testing to help eliminate those measurement errors that they're collecting in their annual surveys and their close zone surveys that they've done. To monitor those polarized potentials that are more negative than that 1.15 and eliminate that error and get a more valid reading to totally ascertain the level of cathodic protection that they have on that system. As part of the procedure to modify their policies and define how they measure those polarization levels and really the formation or decay of that polarization. So when they do their 100 millivolts compliance testing, basically to step away from utilizing their old historical depolarized values and implement more of a process of when they identify a failure of their polarized potential to implement that they depolarize and obtain a fresh set of depolarized values for comparison to define their 100 millivolt polarization criteria. And then lastly, to investigate alternative methods. There's other methods to help measure their polarized and those depolarized potentials. And one of those is being utilization of coupons. They utilize coupons on their transmission piping outside of VMT. The coupons just allow for eliminating some of those voltage errors that they're seeing historically, and it's just another test method and tool that I think they could implement there and be of some use at VMT. So that kind of leads me to questions. I know there's a lot to ascertain in this, but hopefully I did it justice.
Well, thank you, Keith. Is there any questions? I see Jim Herbert has a question.
Thanks, Keith. Electrical stuff always kind of is a mystery to me. I'm glad there are people like you who smile when you talk about it and genuinely enjoy it. My question, we often hear a lot about coupons. Could you give me a coupon 101? Are they working like zincs on a boat? How prevalent are they in the industry? Is it a very simple yet effective way to monitor corrosion? Just give us a basic of coupons.
Sure. So I'll backtrack real quick too. Just you mentioned zincs on a boat. So zincs on a boat is just another type of cathodic protection system where where you use the natural potential of the zinc, which is more active than either the aluminum or hull of your boat, and so that zinc corrodes to protect your boat hull. So that's there. But as far as the coupons go, a coupon's just a small bare piece of steel that essentially represents a coating anomaly or coating holiday on the pipe. So where, you know, your pipelines, their first line of defense is to utilize an effective coating that helps eliminate, you know, provides a barrier from the electrolytes to the bare surface of the steel. So a coupon represents basically a segment of that pipe, and by putting it in the ground, and if we connect it to our structure that's being cathodically protected, that coupon essentially receives that cathodic protection and builds polarization on it. We can then, as we take our readings, we can disconnect that coupon, and that coupon should be free of any other current sources and influences that are flowing through that soil. So you can get a more accurate polarized potential off that coupon that's essentially representative of what that polarized potential would be on the pipe.
Any more questions for Keith? So coupons, Keith, it actually is it's giving you a representative of natural occurring properties of the soil?
But not essentially of the soil, but just what's occurring really on the pipe surface is what it's representing.
I see. So I was wondering how, when you have a CP system like that is functioning, and then they do an internal pipe inspection, if you get erratic readings into such on that, does it prove out when they actually do the internal inspection, and do they see a if you will, something from that inspection that corroborates the information from your CP system that does not seem to be working correctly?
Yeah, absolutely. I mean the inline inspection is just another tool to help collaborate whether you're adequately cathodically protected or not. So I mean, if they perform a inline inspection and they do determine that they have metal loss, and if it's external, and they can, and if they have some kind of regulated period of doing those ILI inspections where they can see if there is an active corrosion, you know, from year to year, are they seeing more metal loss from survey to survey? And then that would kind of lead you to the fact of, okay, maybe the cathodic protection is not working effectively, where there's corrosion still occurring on that pipe. So I mean, it's definitely a tool to use in conjunction with the cathodic protection surveys and testing that's being done. And a lot of times operators will overlay both set of data to kind of see if there's any correlation between the two.
Gotcha. Robert Beadle.
Yes, thank you, Robert. And it was a very good presentation, Keith. As a vessel owner, it's always interesting to hear something along these lines here that pertain. My question is how the cathodic protection is installed. I mean, you're dealing with fresh water on the ground. Do they have a standard for putting it in the ground? You said along the pipelines. Is it sand? Is it rock? Does that varying material, you know, is it in a sump area? More wet than other? Does that have an effect on the current flow on? And
yes, I mean, absolutely. I mean, the soils, the difference in moisture definitely plays an effect. I mean, if it's drier, you have a higher resistance. And so it's going to be harder to pass that cathodic protection current through those soils. And likewise, if you have varying soils where it's wet and dry in locations, I mean, you're going to have different cathodic protection requirements. So the benefit of the linear anode like they have installed, if you think of it as like a leaker hose in your garden, I mean, it provides that water, provides that current continuously along the structure that you're trying to protect. So you can provide a lot more current in that effect. And as it changes, if your soil conditions change from point to point, they have junction boxes and control limits where they can adjust the current output of each leg of that anode to help balance things effectively.
Okay, so there's ways to compensate for different
right
terrain.
Right.
And is there any anodes that are actually, like I'm stuck on a boat, that fasten to the any of this equipment that that go in and be replaced?
So I mean, there's a life. Are you thinking like a life expectancy? And
I'm thinking like an anode on my boat. I go and I replace it every year or as need be. Is there anything like that that's physically replaced or?
Yeah. So and the anode itself it's going to deteriorate as it's giving off that current. So typically in the industry, design life, if we were to design a new cathodic protection system or replacement cathodic protection system is 20 to 30 years. But it's all a factor. It's all a factor of how much current that anode produces, and each anode has a specific life to it based on how much current it produces.
You're talking about a system with the rectifier and all that, but
no,
I'm speaking of a standalone anode.
The standalone anode, so it's like a galvanic system where you utilize so there's no power source. You just utilize the potential of that anode. And the same concept. I mean, that anode is going to have a life based on how much current it produces each year.
Okay, what material do they use? Magnesium, zinc, aluminum?
So on an impressed current system, those kind of anodes will not last very long. So they use another anode. So some of the more not sacrificial, but they're remote type ground beds that they're utilizing. I'm not sure what they have, but they could be graphite, they could be silicon iron, something that has a lower consumption rate per pound per amp of current that they produce. The anode that they have with the linear anode, it's actually like a polymer type anode, which really has a pretty long life to it. But again, it depends on the current output.
Okay, no, that's thank you. A lot to learn. Thank you.
It's easily replaceable, so they'll just trench in a new linear anode, maybe next to the existing linear anode that they have.
Okay. Great. Thank you.
Yep.
So Keith, I was just wondering about the automation of these systems, and you say they take readings maybe quarterly or 6 times a year, but yet they have alarm systems that are integrated into it. And it's probably, it doesn't happen fast, if you might say, that you get a variation that would go to an alarm set point. But at the VMT, are these set points, and are they monitored all the time?
Yeah, with the remote monitoring that they have, so I mean, they can set their upper or lower limit, and so I mean those are monitored every day.
Yeah,
I mean, so it's a continuous monitoring of that, and then I mean you're mainly looking for a catastrophic type where you lost power to the rectifier, then you can get that notice.
Yeah. Amanda Bauer.
Thanks, Robert. I was just going to say to Keith, great report. And if there's no more questions, I was going to make the motion if you're ready for it.
Were there any other questions? Seeing none, go ahead, Amanda.
All right, then make a motion that we accept the report titled Review of Cathodic Protection Systems at the Valdez Marine Terminal by Keith Boswell of National Pipeline Services as meeting the terms and conditions of contract number 5998.19.01 with direction to staff to forward the report to Alaska and state and federal regulators accompanied by a cover letter summarizing findings and recommendations with requests for appropriate action.
And this is Robert. I'd like to second it.
Thank you, Robert. Thank you, Amanda. Are there any objections to this action? Hearing none and seeing none, this report is approved. Thank you. Thank you, Keith. Very comprehensive. Thank you, Austin.
Thank you.
You bet.
It's been my pleasure.
Thanks so much for participating.
Thank you.
All right, let's move on to